Hi everyone. Today I'm going to be talking about machine learning, an extremely hot topic, unlike the weather. It seems that everywhere that you look, you're going to be saying about machine learning. And today I want to talk about the background of machine learning, how simple it is, so that you can actually apply it to your web apps. Today, every web app would benefit from artificial intelligence. My name is Carlos Aguayo. I'm a director of software development at Appian. I've been there for 13 years. It's a fantastic company. And I'm also a master's student in Georgia Tech, specializing in machine learning. I'm also active in Kaggle as a data science competition platform in OpenAI. So if you bear with me a couple of minutes, I want to tell you about what is Appian. Appian, we see ourselves as a world-class elite software company. We proud ourselves of building great software and making the world better. But I think it's better to tell you what it's Appian through a quick video.
Is going to be incredible. It'll take work, we'll have to fight for it, but 2017 could be the best year that Appian has ever had. It's not an ending point. It's another step in a long journey. We look forward to making the rest of that journey with the many friends that we've gathered along the way.
Okay, and with that, so I want to talk about what is machine learning, and first I would like to get input from you. So machine learning is, like I said, a really hot topic. So I was wondering, someone has what's in your mind? What do you think machine learning is? Yeah, go ahead.
Prediction?
Okay, it's actually pretty good. Yeah, machine learning is associated with prediction. Anyone else? So I want to share two definitions. One from Arthur Samuel. Actually, something I find interesting is that this definition is from the 59, almost 50 years ago. Machine learning, despite being really hot right now, has been considered a discipline for over 50 years. Machine learning, according to Samuel, is giving the computers the ability to learn without being explicitly programmed. So right now, when you're building an app, you're programming to do something. Right? But we want the computer to be able to do something without you explicitly programming it. And we'll later be seeing demos where we apply actually this definition. And another definition comes from Tom Mitchell. So imagine that you define a task. And to do that task, you can measure it by some performance T. How good you can perform that task. Machine learning is that if you give it experience, the more experience that you give, the better the machine will perform at that task. So it's not that you're programming at it, you're just giving experience and it's making it better and better. I know that this might sound a little bit vague, but I prefer that we actually do demos and make this thing dynamic. So the first one, let's see, I took this exercise from a place called primary objects. An exercise that I like a lot. So imagine that we're tasked with creating a program that can detect if a voice is from a man or a woman. Initially that might sound a little bit complicated, you might have to do some analysis, but I want to show you how easy that is with machine learning. And for that, I want to make this fun. I want 2 volunteers. So let's, if you wouldn't mind, a guy and a girl to actually speak, and let's see if your voice can be detected. Any volunteers? Don't be shy, guys. Go ahead. Yeah. I need to step down and talk to the computer.
So we come down right now?
Yes, please. Thank you. And I need a girl. Yeah, okay. So what we're going to be doing is, thank you for volunteering. These folks are going to be speaking to a computer, and we're going to detect if they're, hopefully the computer will be accurate and predict if their voices are from a man and a woman, and then I'll show you how we're doing that. So, first person, come. So what we're going to be doing is, I'm going to hit record, say something, hello world, how are you, it's called for, I don't know, 3-4 seconds, and that's it.
How's it going? My favorite sport is basketball. I love the Toronto Raptors. They're the best team. And this course is great.
Awesome. So let's save that audio. What's your name?
HeKNearest, S-H-A-N.
Okay. Now let's record. Yeah, same drill. You just need 5 seconds.
Hello everyone, so building on the sports theme, my favorite sport is tennis, and I'm also really happy to be this class and hope everyone is having a great day.
Thank you. And if I can have your name. Thank you, Maddie. And you have shirts here, so thank you for your help.
Yeah.
So, okay, so now we have, there should be 3 sizes, I think. Thank you so much. So, let's see. So we have here Shamir. You're using Wi-Fi, and we have Matt. So what we're going to be doing, the way this is going to work. Yeah. So for each voice, we're going to measure some properties. Typical properties of a voice. So, for instance, we're going to be measuring the mean frequency in kilohertz, the standard deviation frequency. We have a list of, I think it's around 20 properties for an audio. And so, if you see here, for Shamir, we have this set of properties. These are the numbers that I showed you before, and let's do the same things for Maddie. Okay, so we got measurements for both voices. Let's take that's interesting. So these are the properties for Shamir. So paste those things here. Shamir. Bless you. And Maddie. So let's run this code. Just take a second. Yeah, so you can see Shamir, it's a man, Maddie, it's a girl. The computer was able to detect them pretty well. I want you to notice a couple of things. So this is the code. This is what I have to do to detect quickly if the voice was from a man or a woman. More explicitly, all I have is a CSV file. That CSV file is you have it. You can see it here. It's a CSV file with recordings. Specifically, I have 3,000 recordings, measurements, half men, half women. So you can see that the same numbers that I was getting before for you, I have them here, and each row is labeled as female or male. You can see the ones the first half is male, the second half is female. Then I have a machine learning classifier, and I just ask for it to fit all the voices that I've seen into the labels that I give it. And now I can just use that model to predict if your voice is from a man or a woman. I didn't have to go and learn about acoustics, audio, do any complicated model. Very quickly, I have something that the task is to detect if the voice is a man or a woman. It has actually the performance is really, really accurate. It's 99%, and you saw it live in a demo. Now, the question is, well, I mean, how can we, how did this actually work? Initially, for many people, one says machine learning, and one thinks, well, it's obviously it seems like magic. Obviously, it's not magic. What did we do? So we took, like I said, 3,000 samples, and we gave it to a machine learning algorithm. That algorithm is giving us a function, a model, a function that we can later give a new instance, run it through that query, and tell us if the voice is a man or a woman. But again, now the question is, well, I mean, what is this guy really doing? And I want to show you that it's actually very, very simple. So let's do another simple example. Imagine that you have this partition 2D plane X and Y, and then you have this dot. I don't know, it's X 100, Y, I don't know, 150 or something. Given an X and a Y, do you think that point is pink or blue? Anyone let's give it a shot? Yeah, of course. You cannot know. You don't know. You don't have any way to tell if that's pink or blue. How about now? Who wants to tell me what that point is? It pink or blue? Yeah, blue. Right. So they required that much to do it. But I'm curious. How do you figure out that that was a blue? Rupert? Yeah, that's actually well, I mean, it's obviously not magic. One very simple approach is, well, I mean, just obviously this point is very close to other blue ones and very far from pink ones. That very simple algorithm is actually called HeKNearest Neighbors. It's one of the simplest yet very effective machine learning algorithms. Many things that you actually see today is called machine learning and seems to be really fancy. It's actually just doing this thing. You have a lot of data. You want to run a prediction that we said before. That prediction is just saying, well, I mean, I predict that this point is going to be blue because everything that is very near to it is also blue. There are, of course, some other more elaborate ways to do it. One could say, well, I mean, let's just draw a line. I mean, there's a line that clearly everything here is blue, and here everything on the top is pink. That's called support vector machines. And there's another one that's also very simple. One can say, well, I mean, let's just build if X is larger than something and then Y is larger than something, it's pink, else it's a blue. These are called decision trees. All these three algorithms that look deceivingly simple are used very, very often in machine learning. As a matter of fact, the example that we just did, this is the decision tree for detecting if the voice is a man or a woman. One might have expected a really complex tree, and in the end, I mean, something really, really small. Okay, so one would say, well, what's the difference, right? I mean, this is, Carlos, I mean, this is something really, really simple. You're telling me that this is what the computer does. Like, when it does these amazingly complex things, what is that it's doing? The difference is that, at least in the examples that I gave you, for a human, it's very easy to see up to 3 dimensions, maybe 4 dimensions. Whereas a computer can see in a high dimensional space. When I show you that CSV, I show you we had 3,000 dots, but we had, how many dimensions do you think that that space had? Yes. This, yeah, it has, I don't know, here it's like 20 dimensions. So imagine you as a human trying to see that. It's something really complicated. I don't know if we can visualize it, but a computer can visualize it almost instantaneously. In this 20-dimension space, the computer can quickly see a model that differentiates these two classes with as the same, as easy as you were able to distinguish these two. So hopefully so far simple. What we did right now, it's called supervised learning. Within machine learning, one of the largest spaces right now that is the one that you see left and right, if you hear anything in the news, is mostly supervised learning. Supervised learning is the task of inferring a function from labeled training data. So training data is obviously a set of training examples. In our example of voice, we gave 3,000 voice samples. That was our training data. And then each example has an input object, so it has some measurements, something, and an output that was saying, well, I mean, if it's a man or a woman. And then all we have to do is a machine learning algorithm takes that data and figures out a function, the same way that you did it before with the examples. I want to take a few minutes and talk about neural networks. So neural networks is something that is also really hot and old. Neural networks have also been around for more than 50 years, and it's also within supervised learning. But the concept behind neural networks is actually really simple. I was reading the other day that if, I'll tell you in a second. And I want to explain that by another simple example. Imagine that you want to figure out if you want to predict or decide if you want to go to a party tonight, if you want to go out. And a way that you can figure out that is, well, I mean, you would ask yourself a couple of questions. So maybe your decision will depend if you can actually wake up late tomorrow. If you have to be out really, if you have to be in some place really early, maybe you don't go out. Maybe a question that you would ask is, well, I mean, will my crush be there? I mean, if you're interested in one person, I mean, it doesn't matter, you're going to be up late, you're most likely going to be there. You'll be interested if you're knowing if your friends are there. Maybe you have another class tonight, maybe you have gone to that place before. Basically, to answer your original question, you ask something else. And in the end, what you do is kind of a weighted decision. And for instance, in this example, let's do that weighted decision. And for example, let's say, well, if my crush is there, I have high value for that. I don't care for anything else. If that person is there, I want to be there. My friends and let's put a threshold of 10. So if my crush is there, I will automatically go. If my friends are there, that's important for me, but just not enough for me to go out. I would have to think that my friends are there, and also I have to go, I can wake up late. So, for example, is my crush there, nothing else matters, yes, I'm going to be at the party. Can I wake up late, but everything else is a no? Well, I mean, if my friends are not there, my crush is not there, no, I'm going to take a rain check. But if I can wake up late and my friends are there, yeah, I'm going to be there. And then the output is a 1. What we just did is called a weighted decision, but it's also called a neuron. And the reason why it's called a neuron is because, first of all, this resembles the way that our neurons in our head works. We have several inputs into a neuron, and depending of the inputs, you can excite the neuron and activate it. And not only that, you activate it and you connect it to other neurons. So the power of a neural network in your brain and everything else is when you compose many things, like threads into like many threads. So this is what a typical neural network looks like, but it's exactly the same as the one that we were seeing before. So if you remember, we had our inputs, and those inputs had a weighted decision where this was our output. And in a neural network, we're doing exactly that. It's just that the output of this thing, it becomes the input to something else. And the output of that thing becomes the input to a final output later. And when you combine all of them, it gives you very powerful things. the reason why neural networks are really are expected to be really powerful, there's a mathematical proof that says that a neural network can model any mathematical function that you give it. So in the examples that we were seeing before, you could separate the two-dimensional space with a line. And obviously, there are functions that cannot be done with a decision tree, or maybe with or maybe it would be complicated to do it with nearest neighbors. Technically, a neural network can just do any function. It's just that, well, I mean, it might require a lot of time to train it, and maybe you don't know the topology. Topology is, well, how many neurons you have to put in order to get that function. I also want to talk about 1 second about deep learning. So deep learning is even the harder topic than machine learning. And deep learning, all that it is just neural networks, just make them larger. So whereas before, in here we had a neural network, and you can see that there's like layers. We have our input layer, and then something that is called a hidden layer. And here we have 2 hidden layers of neurons, and then an output layer. Remember, in the end, I mean, these neurons are exactly a weighted decision. There's nothing different from being here than in any of these layers. When you stack, in a very naive way of explaining it, when you stack many hidden layers, that's where you have a hidden deep learning. That's where the deep is coming from, having many hidden layers. And on top of that, deep learning is very convenient for images. The way that you predict, for instance, when you have an image, if you want to predict if it's, say, a cat or a dog, you can just literally pass each pixel as an input to a neural network that is going to tell you, well, is the image a cat or a dog? And just a plain neural network is actually very efficient, very good at detecting those things. But the rise of machine learning happened in 2012 when a professor called George Hinton created, won a competition where he used something called convolutional neural networks. If you pass an image into a neural network, well, you're just passing each pixel. But there's no way for you to tell, well, what's the relationship between the pixels that are near to each other, and that's what convolutional neural networks do. So you take an image and it passes a patch into another layer. The high level, that's what I'm just gonna explain. Now, high level summary for supervised learning. You have labeled data, again, many examples, each of them saying you're a man or a woman, it's a cat or a dog, it's green or blue. And what you want to do is learn a model that can predict those seen and unseen examples. And obviously there's no magic. Now, I want to, the second part, I want to talk about what I would claim it's actually the future. Right now, like I said, I mean, it's really hot, deep learning, supervised learning. But there's something else that is emerging, and I don't think that the news or the media has given it enough attention. So, first of all, a very important milestone that happened amazingly 20 years ago was that we were finally able to defeat Grandmaster in chess. 20 years ago, IBM was able to create Deep Blue. But there were a couple of, I would say, caveats or controversies from Deep Blue. First of all, the system derived its playing strength mainly from brute force. Then the chess knowledge was fine-tuned by grandmasters. It studied thousands of games, and at the competition, for instance, IBM was given the chance to tune the machine among games. I mean, the Deep Blue play, I think it was 7 or 5 games against Garry Kasparov. In between each game, IBM had the chance to fine-tune it. So I don't want to belittle it. It was a great achievement. We were able to defeat a grandmaster, but still, there was something that all of us wish, okay, it could have been smarter or better. So, so now I want to talk about Go. Go is a simpler game than chess, but unlike chess is already, I mean, the space for chess is already really big. I mean, there are, I don't know how many possible board games, places. Go is even more complex. And 2 years ago, in the news, there was a company called DeepMind that was acquired by Google where they created AlphaGo, a computer program that was also able to defeat the human champion in Go. And it was obviously even a more important milestone because the Go is obviously more complex than chess. But it was also based on the same thing. It had like a high computational power, and it was fed with great evaluation functions. However, last year, just less than 6 months ago, DeepMind created something called AlphaGo Zero. 2 years ago we had AlphaGo that defeated the champion, and 6 months ago DeepMind created AlphaGo Zero. At the beginning of where it started doing something called reinforcement learning that we're going to see in a second. At the beginning of, I would say, time for AlphaGo Zero, 0 days, you can see that it doesn't have any prior knowledge of the game, only the basic rules as an input. You don't teach him games, you don't teach him anything, just say, these are the rules, start playing with yourself. 0 days, obviously doesn't have anything. After 3 days of just playing with itself, AlphaGo Zero has better abilities than AlphaGo. So again, 2 years ago we had one of the highest milestones in AI by defeating a champion in Go, but we had to feed it with many things. In here we have a computer program where we didn't give it anything other by itself, and in 3 days it's able to defeat that champion. 21 days it increases its ability. 40 days it increases the ability, surpasses all other versions including AlphaGo Master. Entirely from self-play, no human intervention, and not using historical data. Then we have also from the same people, DeepMind, and a clever guy called David Silver. Notice that this paper is from a month ago. This is really cutting edge. Mastering chess and shogi. So a month ago, these guys published a paper